Okay, so now for the last, I'm not sure, hour or so, maybe 50 minutes, we're going to talk about MOI. It's been mentioned a lot over the last 2 days, and some people know a lot about it, and some people know very little about it. And I kind of provocatively titled this a comprehensive overview. So MathOptInterface is the layer that sits between JuMP and the solvers. So at the top, there's JuMP as like a user modeling language. There are other user-facing modeling languages in Julia. There's convex.jl, which has been around for a long time, optimization.jl, and maybe some others. They all lower to this intermediate API called MathOptInterface. And then below MathOptInterface, all of the solvers write to the same API. And so there's the highs solver and the highs.jl package, which talks between the C interface of highs and MOI. There's one for SCS and IPOpt and Gurobi and Cplex, and every solver has its own package and its own interface to this MathOptInterface. Why is this talk needed? MOI is one of the largest packages in Julia. Everybody uses it every time they solve a JuMP model. It has some very novel stuff in it. It has a lot of stuff in it, as we'll kind of get to. And we've never really given a talk about it at JuMP. There's not much there's a paper about it that we wrote. There's the online documentation, but there's no kind of easily accessible overview over it on YouTube. So hopefully this is what this will be. I hope by the end of this talk you kind of understand why we wrote MOI and why it's as large as it is. We've talked about bridges a couple of times over the last 2 days. We'll go through what a bridge is. And you kind of have the gist of what is in MOI, but we won't have any kind of low-level details of what it actually is. So in the beginning, there was MathProgBase. And MathProgBase divided the world into three things. There was a class for linear quadratic problems. There was a class for conic problems. And there was a class for nonlinear problems. And each solver could choose one of those three classes to code to. So Gurobi and Highs and stuff chose the linear quadratic class. Conic solvers like SCS and MOSEC chose the conic class, and then nonlinear solvers like Nitro and IPOpt chose the nonlinear class. And there were two kind of bridges. There was a bridge from linear quadratic to conic, so solvers like SCS could solve a linear program. And there was one from linear quadratic to nonlinear, so things like IPOpt could solve LPs and QPs. But there were many problems with MathProgBase. The first thing, if you've ever kind of looked into the details of solver APIs, is you realize that even though there's kind of standards, there is no standard. And the closer you looked, the more differences you found. And so even like the exponential cone, ECOS and SCS have a different permutation of the order in which they expect the exponential cone. Gurobi supports affine constraints or linear constraints with a lower bound and an upper bound. But when they add that, you have to add it via a special API and introduce this intermediate variable, and it kind of mucks up the order of the variables. So it's kind of easier for Gurobi.jl not to support bounded linear inequalities. CSDP doesn't even support adding a free variable. It only can support adding non-negative variables. And then there were solvers that kind of mixed these three problem classes. So Nitro was nonlinear, but it also supported the second order cone. And Gurobi was linear quadratic, but now it has some nonlinear features. And so these three kind of buckets were not enough to describe all the differences that there were between solvers. The three buckets also were quite hard to add new features to. So at the time, we didn't support indicator constraints. We didn't support complementarity constraints. And we kind of had no plan for that to work. And then at the end, we'll talk about this caching optimizer and how we support in-place modification. And MathProgBase had some support for modifying persistent solvers, but it was a bit complicated. And our goal with MOI was kind of to fix all of those four things. So in 2017, Miles organized the first JuMP-dev workshop with Juan Pablo. And the core theme of the workshop was, should we release JuMP 1.0 and declare success and victory and maybe kind of go off into the sunset? Or should we throw everything away and rewrite it from scratch? And we chose the second option, and then spent the next 3 years or 4 years kind of regretting it, but kind of plowing our way through in the end. And the design we settled on was a new abstraction. Instead of the 3 buckets of linear, quadratic, conic, and nonlinear, we decided to say that an optimization problem is I want to minimize some function of x, subject to some constraints, which are a function of x lies inside a set. And we can define a very small set of functions and a very small set of sets. And then by mixing and matching these functions and sets, we can come up with different types of problems. So a binary variable is not just a binary variable. It's really the constraint that a variable index x lies inside the set 0, 1. And maybe a bound on x is the variable index x lies inside the set greater than 0. And a linear equality constraint is the function scalar affine function lies inside the set equal to. Vector functions, vector affine function lies inside the set non-negatives, and then there are cones, and even kind of PSD matrices and many others. Instead of choosing one bucket or one class for a solver to live in, solvers can declare very fine-grained support for what functions and sets they do support. So highs can say, hey, I support a scalar affine function in equal to, in greater than, in less than, and interval. It knows about variable index lying in equal to, greater than, less than, interval. It also knows about variable index in 0, 1, which is a binary variable, variable index in the set integer, which is an integer variable, in the semi-continuous set, in the semi-integer set. And then it knows about 2 different types of objective functions. It knows about the scalar affine objective function and the scalar quadratic function objective function. SCS says, hey, I know how to support vector affine function in non-negative, 0, second order cone, and a bunch of different cones. And I know how to support the scalar affine function and the scalar quadratic objective function. Notice it doesn't know how to support variables with bounds. It doesn't know how to support scalar affine function. It only knows how to support vectors in these sets. And then IPOpt says, hey, I'm a nonlinear, local nonlinear solver, so I know how to support variable index with lower bounds and upper bounds, equal to interval. It can also support a variable index in parameter, which is how we do parameters in optimization problems. And it can also support scalar affine function in the same sets, scalar quadratic function in the same sets, and scalar nonlinear function in the same sets. There's a new set that we added that Robbie talked about in the MathOptInterface talk, which is vector of variables in this vector nonlinear oracle set, which is a special thing that we added that IPOpt now knows how to support. And then for the objective function, IPOpt knows how to support variable index, affine functions, quadratic functions, and scalar nonlinear. And so this allows us to have very fine-grained control on what functions and sets and objective functions each solver supports. The downside to this is somehow now users and solvers need to agree on what functions and sets they will use, because there are multiple ways of writing down the same problem. The user might write down, hey, I've got a variable x lies inside the set greater than, but the solver might have said, I only know how to support vector of variables in non-negatives. And even though they're kind of the same thing mathematically, one of them is a scalar function and one of them is a vector function, and they're kind of different functions and sets in MOI. There are also things like second order cone and rotated second order cone that are affine transformations of each other. So if a solver supports a second order cone it can support a rotated second-order cone by some affine transformation, but the user and the solver would have to agree on which one that they were both going to use. And then there are other ones that are kind of much more complicated transformations that maybe have to introduce new intermediate variables and constraints. But there is some mapping between, say, a log det cone and a bunch of PSD cones. So we came up with the idea of these bridges. And a bridge is a mapping between a function and set constraint into a set of new constraints, which are of different types. And it might also add some new decision variables. So a bridge is a mapping between a function and set constraint into a set of different constraints. Each bridge also implements ways to like delete the bridge and some getters and setters to pass attributes from one side of the bridge to the other and back again. Maybe they're primal starts, primal values, and dual starts and dual values. So one example of a bridge in action is this model. We're using highs as the solver, and we've written down the constraint that 2x plus 1 lies inside the set integer. So this is not normally a constraint that you might write down in a typical mathematical modeling package. And highs doesn't natively know how to support this affine function lies inside the set integer. And typically what you might do is you might go away and say, hey, I know how to reformulate this by hand. I need to introduce a new decision variable y, and I need to say that the 2x plus 1 is equal to y, and then y is equal to an integer. Behind the scenes, that's exactly what this scalar slack bridge does. It does it underneath inside MOI. And so if you made that model and then say print the active bridges, it says, hey, this constraint scalar affine function in integer is unsupported, but I was able to bridge it using the scalar slack bridge, and I added a new constraint scalar affine function in equal to, and I added a new variable integer. And then if you print the model at the bottom, it's exactly the same model that you would have written by hand if you did that transformation manually. So we kind of have a view of the world where on the left-hand side we have users, and on the right-hand side we have the solver. And the user is going to write down their JuMP model using a set of, well, a list of constraints that have different functions in different sets. And on the right-hand side, the solver has declared, hey, I know how to support this list of functions and sets. In the ideal world, the user and the solver agree on which functions and sets to do. So the user writes down a scalar affine function in equal to, and Hi says, yes, I know exactly how to support that. In that case, we just pass the model from the user to the solver, no problems. If the user and the solver disagree on the function and set chosen, then maybe we can transform the constraint via a single bridge, like the scalar slack bridge, where we take the model from the user, we maybe make one small change to it and pass that to the solver. But you can think that these bridges also nest together. So maybe we can take a function and set written by the user, we can change it into a different type of function and set, and then maybe that can be bridged to two separate constraints inside the solver. And so it's really a graph of each constraint is a function and set which is a node in this graph. The users want to add a node in the graph. Solvers know how to support some of the nodes in the graph. And we want to find a chain from the user to the solver with a set of transformations to turn the user's problem into a problem that the solver knows how to deal with. And this graph is really a kind of messy, directed graph with lots of arcs between all the different nodes that correspond to different types of constraints. So the question is, like, which path through the graph should I choose? Because this is kind of now it's an optimization problem. And we solve this problem by solving a shortest hyperpath problem through this graph of bridge transformations, where this graph is a graph, and the nodes are constraint types. The edges are these bridges, and a bridge might have kind of more than one arc leaving it. The source node is the node that the user wants to add. The target nodes are the nodes that the solver knows how to deal with, and then there are weights on the edges. Choosing the weights is an open question. for now, we've pretty much just said each bridge is worth weight 1. But you could probably see that if there are multiple ways you could rewrite a constraint, some of them might be preferable to others. And so in a few cases where there are multiple ways to reformulate the same constraint, and we know that one of them should only be used kind of if anything else fails, then we've made that weight 10. But how to kind of tune the weights in this graph is an open question. And so when you say add constraint and you want to add the constraint to the model, behind the scenes we solve this shortest hyperpath problem to figure out which set of bridges to use to transform your constraint into a set of constraints that the solver supports. And in this case, we might have taken the graph and solved that shortest path problem and found out that that was the most efficient way to rewrite the user's constraint into a set of constraints that the solver understood. I've kind of been lying to you for the last few minutes, and that the problem is actually more complicated than it seems. We have been talking about constraint reformulations. So these are constraint bridges where we're turning a constraint into a different type of constraint. There are also objective bridges. So when we add an objective function, the solver might not support that objective function. And a common one that comes up is if the user writes down a quadratic objective function, but the solver is, say, a conic optimization problem, and it only supports an affine objective function, but it supports like a second-order cone or a rotated second-order cone. There's a way we can rewrite that quadratic objective function into a problem that the solver understands. And in this case, we're going to add a new decision variable t into an epigraph reformulation where we're now minimizing this new decision variable t subject to the constraint that t is greater than or equal to x squared. But t greater than or equal to x squared is a scalar quadratic function inside the set greater than. And maybe the solver doesn't support that constraint type. It actually supports scalar affine function in rotated second order cone. So then there's another bridge from the scalar quadratic function constraint into a rotated second order cone constraint. There are yet more types of bridges. So there are constraint bridges, there is an objective bridge, there are also variable bridges. And so at the start I kind of told you that CSDP did not support adding free variables. It can only support x or is non-negative. So what happens in JuMP if you write down @variable of x, and x is a free variable? We actually have to add 2 decision variables to CSDP, both of which are non-negative, and then anywhere that x appears in JuMP, we have to replace that with x1 minus x2. This is like some of the most complicated code in all of MOI, is working out where to do these substitutions, keeping track of them, and then making sure we get the solution from the solver and the duals back to the user in the right form. And Benoit added this code in 2019 in a very long PR. And Miles quickly read it and said, I don't have any comments, looks good. So maybe just to repeat this for YouTube, because it's kind of funny. Benoit says that when he first tried to open this PR, it was one very big pull request, and Miles told him not to do it because then there would be only one person who understood the code. So we broke it down into many small pull requests. And Miles said, no worries, they all look good. But there was still only one person that understood all of the code. And so I like to kind of use this image of JuMP in my head. On the left side, we have the user's model, where they've written down some objective functions, they've written down some constraints, which are these functions and sets, they've written down some variables, which are just x in a set. And on the right-hand side, the solver has chosen itself which set of functions and sets that it supports. And in the middle is just chaos. Benoit's Bridge-Bellman Bedlam is what I managed to come up with. I also used my meme skills to come up with this, because anytime there's a bug in MOI, it often leads back to the bridges, and then I get kind of stuck in the code looking around and trying to put myself in Benoit's shoes in 2019 and understand what he did. And so Miles is up the top, the BDFL, the benevolent dictator for life, saying, this looks good to me, as Benoit is giving just us the gift, which is a nice gift, but there's lots of future maintenance associated with this. And I'm not saying that we should not have added variable bridges, but we should have thought very deep and hard about how much work it would add over the following years. So MOI is a Julia package, and most Julia packages are actually pretty small. You don't have to write that much Julia code to be able to do a lot of stuff. MOI is over 120,000 lines of code. 79,000 lines of code of that is in the source, and there's about 43,000 lines of code to test MOI itself. Breaking that down, the bridges as a submodule within MOI is about 20,000 lines of code, so a quarter of MOI is the bridges. And then the testing of the bridges is almost half of our tests. Another thing inside MOI is this test submodule. So as a solver abstraction, we also provide solvers with a lot of tests. And so kind of another quarter of our source code is tests for other solvers. We'll go through each of these submodules in a bit more detail. There's also one for file formats, some nonlinear stuff, and then this utilities thing at the end, which has turned into the kind of place where we put all the other stuff that we didn't really know where to put. MOI is written in Julia, and we use multiple dispatch a lot. So every solver is a new type. Every function is a new type in Julia. Every set is a new type in Julia. There are attributes that are different types. And they all overload a very small set of functions, but we make many different overloads or methods of a single function. So there's like a add constraint, takes in a model, a function, and a set. But then for every optimizer, for every model, for every function and set that it supports, there's a different method that we add. And to kind of give some idea, running the tests for MOI takes quite a long time. When you run the tests, over 6,000 different functions get compiled. This is different named functions. And there are over like 370,000, almost 400,000 different versions of each method that get compiled. It's a lot. The functions, we break them down. There's a kind of abstract function type at the top, and then we break the functions down into abstract scalar functions and abstract vector functions. A couple of examples, like there's the variable index is a scalar function, which is just a single variable. And then a scalar affine function is a vector of scalar affine terms, which are themselves a coefficient and a variable, and then a constant. So this is an array of structs design. We had kind of talked about doing a struct of arrays. We went with an array of structs, and it seems to be working okay, but there are pros and cons to that. We kind of occasionally just talk about different ways we could use represent these data structures, but these are working well. For sets, we have the same breakdown. We have an abstract set type at the top. We have an abstract scalar set and an abstract vector set. So like the set equal to is parameterized by the number type. It just has a value. The second order cone has a dimension, which says what is the dimension of the input vector. So if I have f of x lies inside the set second order cone, what is the dimension of f of x? There's a set for SOS1 constraints. These have data associated with them. So an SOS constraint needs to have some ordering of the input variables. So that is the weights that are in that vector. And then there are also kind of sets which are themselves composed of other sets. And so the indicator set says, hey, this function f of x is true if and only... the indicator set says, hey, this function f of x lies inside the inner set if and only if this z variable is true. Going into a bit more detail of each of the submodules within MOI. The bridges submodule is, as we kind of said before, like the largest and most complicated thing in MOI. There are the three different bridges that we talked about: constraint bridges, objective bridges, variable bridges. At the moment, we have about 76 different bridges, which are different reformulations from one constraint to a different type of constraint, an objective to a different type of objective, or a variable to a different type of variable. There is this lazy bridge optimizer object, which manages all of the graph and finding the shortest path and all that sort of stuff. And then there's a bunch of tests. The good thing for users is you don't really need to know anything about all the stuff that is hidden in there. You just say, hey, I want to instantiate a new object of the highs.optimizer. And I say with bridge type equals float64. And then you get a thing that is magically doing all of the bridges and the reformulations and the shortest path behind the scenes. The bridges are pretty horrific. So we've kind of just gone down the road of just testing them a lot. I think now we're in a very good place where I haven't found a bug in one of the bridges in a while. So we test every bridge kind of in isolation with a set of tests on the right-hand side, which says, hey, you've got your input problem. So the 0,1 bridge takes a variable x in 0,1, and instead of adding a binary variable to highs, say, it adds a new decision variable x in integer, and then it adds a scalar affine function. 1 times x lies inside the set interval. We could have added bounds instead of the scalar affine function. We could have just said that x lies inside the set interval, except then there would be a conflict with if the user had separately provided bounds on their binary variable. So in some places, we add a scalar affine function in the bridge, even though a bound might be preferable, and then we rely on the solver to pre-solve that later. So we kind of test every bridge in isolation like this. We also run a very wide set of unit tests for every solver. And then before we release each version of MOI, we test every single solver that we know about to ensure that we haven't made any changes to MOI that broke any of the solvers. This is kind of still sometimes not enough, and often if there's an issue in MOI, it's often an issue in the bridges. There's a whole submodule on file formats. So this is how we can read and write JuMP models to disk. At the moment, we're supporting 6 different file formats. There's the conic benchmark format, the LP, which we talked about, Mars talked about. The MathOpt format is our custom format for serializing JuMP models or MOI models to disk. There's the MPS format, the NL1 for nonlinear, and then the SDPA. There are multiple ways that we could have decided to implement file readers and writers. We, following the kind of multiple dispatch philosophy, decided to implement it by each file format defines its own model type, and then they implement read and write for that model. And so in JuMP, when we say write to file, what we actually do is we create a new destination model object. Then we copy your model into the destination model, maybe reformulating it via the bridges if we need to, because the model you wrote down doesn't exactly fit the file format. And then we write that to file. The biggest downside of this is when you say, JuMP.write to file, we have to copy the whole model first into a new format, rather than just parsing your model as it is. So there's some overhead in JuMP to writing files to disk that might not exist in other places. And the same when we read a file from disk, we first read it into one of these models, and then we copy it into a new JuMP model. I briefly mentioned MathOpt format, and you should go and if you haven't seen it, you should go and have a look at it. This is a JSON file that allows us to serialize any JuMP model to disk. It has a schema, so there's no issues with this parsing and trying to work out differences between how solvers interpret LP files or MPS files. It's pretty simple. Our objective function is a key objective. In it, it has a sense. We're either minimizing or maximizing. And then there's a function, and we know how this function is the scalar affine function with that list of terms and the constant. It's effectively the MOI data structures serialized directly to JSON. And the constraints in our model are just the constraints key with a list of function and set pairs. There's the nonlinear submodule in MOI. This has a lot of stuff that we've been kind of talking about as well over the last 2 days. There's a whole modeling and another whole modeling interface in that for writing and building nonlinear optimization models. There's a reverse AD submodule for doing automatic differentiation on that nonlinear.model object, and it includes all of the coloring stuff that Alexei was talking about. There's also symbolic AD in there for doing symbolic automatic differentiation on JuMP models. If you have a JuMP expression, maybe it's a scalar nonlinear object, we can compute derivatives of that. And there's some simplification and substitution rules in there for simplifying nonlinear expressions. But rather than go into detail on that, you can see previous JuMP-dev talks, both called Improving Nonlinear Programming Support in JuMP, which I gave in 2022 and 2023. So that's a good place to start if you want to know more. I think one really key part of MOI is this MOI.test submodule. And this submodule contains tests for solvers to try and check that they all implement the MOI API correctly. So on the right, we can see the result of running highs over these tests. You say MOI.test.run tests. You pass in an instance of highs and a conflict object, and it goes away and cranks through 3,500 tests in 4.5 minutes. Every time we find a bug in one of the wrappers or a bug in one of the solvers, we add a new test to MOI, and then that kind of flows through into the rest of the ecosystem. So if we find a mistake in highs or we find a mistake in Gurobi, then we kind of testing the other solvers as well. And we kind of semi-regularly find bugs in solvers themselves because of these tests. There are a couple of downsides to how we did this. The first one is we called it the module test, which conflicts with base.test. And a couple of things I had to change to kind of work around that. So maybe we could have come up with a better name, because inside we have like module test and inside using test. And then Julia gets a bit confused about which test we're referring to. And then there's a lot of code in here that gets loaded anytime someone is using JuMP, even though they're not testing the solver when they're just writing and solving their model. So maybe we could have split this out into a separate package rather than having it as a submodule that is inside MOI and gets loaded every time. But we kind of went with the monorepo 122,000 lines of code approach, and it's probably too late now to split it out without breaking a lot of downstream packages. But people keep asking me too, and I keep telling them, maybe not. And then there is this utilities submodule, and it contains a lot of stuff. And it contains a lot of stuff that we find useful, but we don't really know where to put it. And so it just gets put in here, and then it gets referenced from the file formats and the nonlinear thing and the bridges thing, and it's kind of just a catch-all for where to put things. It has some utilities for making it easier to work with some of the functions in MOI. So it includes a lot of like overloads. So you can build up scalar affine function by going 1 times x instead of the full type constructor. It includes this mock optimizer. So one of the problems we have in MOI is we wrote a bunch of tests that are 25% of the source code. We need some way of testing those tests to see that when a solver later tests them, there's not a bug in the test. So we had to come up with this like mock optimizer, so when we're testing MOI's tests, we can kind of pass in a solver that we know works. Yeah, it's for testing. Miles says it's for testing other things as well. Yeah, it's for testing. We use it in a bunch of places in MOI to test MOI without needing a solver. JuMP uses it as well, yeah. Yeah, so that, yeah, and Benoit says, yeah, then there's a tricky index map in it. Yeah, so it's in the utilities submodule because it gets used in a bunch of places, and there's kind of no better place to put it. It could perhaps have lived in MOI.test rather than MOI.utilities. There's also a caching optimizer, which we're going to talk about in a little sec. There's a utilities.model, which is our big problem now is we've got this very flexible data structure of functions and sets, and we need some way of easily writing models. And so this model object knows how to support every function and set that MOA knows about. And then if our other problem is if third parties define new functions and sets, we need some way of storing them. So then there's this universal fallback layer as well, which knows how to support less efficiently than the model, but any function and set. Another thing that a bunch of solvers need when they're writing wrappers is some way of storing indices. So like if I add a variable, it's column 1. I add another variable, it's column 2. And as I keep adding new variables, I'm effectively making a list of variables. But then when I start deleting them, I start to have holes in my vector. And so we need some efficient data structures that can let us grow linearly as we're kind of say adding new variables and constraints. And then once we start deleting, it switches to a different data structure that can represent the holes more efficiently. So this clever dict is really a vector until you start deleting things, and then it's really a dictionary. And then the last thing is there's this generic model thing. Many solvers have a matrix view of the problem, whereas MOI is really a row-based or constraint-based view of the problem. And so there's a way that you can turn a set of affine constraints into a sparse constraint matrix that's pretty much of the form that, say, CLP or CBC need or SCS needs. So I also want to talk about this caching optimizer in a little bit more detail. We've kind of talked about this a little bit over the last 2 days. It's been hinted at that there are kind of persistent optimizers, and then there are kind of these one-shot optimizers. And we often build an optimizer or a model instance, and then we want to modify it. But only some solvers know how to modify their problem data. So in highs, we can build a model, and then we can say, change this right-hand side, change this bound, change this problem coefficient. That's not a problem. But SCS just says, you need to give me all of the data up front. And then once I've built, okay, SCS now has an update thing, but we haven't really implemented that in the Julia package yet. So it says, give me all of the data up front, and then if you want to make a change, you have to give me all of the new data in one go. And this makes it hard if you're writing algorithms like the STDP algorithm, where we're kind of solving a problem, changing a bound, adding a constraint. We want some way of abstracting over solvers that either know how to modify the problem in place, or they don't know how to modify the problem in place, and we need to pass them a whole new copy of the model every time. And this is what this caching optimizer does. Inside, it has 2 copies of the problem. It has a model cache, which is going to be the model that we always keep, and we can modify this ourselves. And then there's this optimizer, which is the, either highs or SCS. And we kind of want to keep the cache and the optimizer in sync. And if we can modify the optimizer, we want to do that. Otherwise, we want to throw it away and build a new optimizer from the cache. So here's the flow of, say, adding a constraint. At the top, the user calls add constraint to this caching optimizer. And then the caching optimizer says, hey, cache, do you support this function and set constraint? If no, maybe you've asked it to add a constraint that we can't bridge, the solver doesn't know how to support, there's nothing we can do here, so we just say, error, we can't support that constraint. Otherwise, we add the model, the function and set to the cache, and then we say, hey, is our optimizer currently attached to the cache? If it is, or if it isn't, there's nothing we can do. There's no optimizer yet. We're already done. If it is attached, we need to say, hey, optimizer, do you support this function and set? If no, we error. Otherwise, we try and add the constraint to the optimizer. If it's an optimizer like highs, it says, yes, I can add a constraint after maybe I've already solved the problem. If it's SCS, it says no. If it's a no, we error, and then we throw away the optimizer and then rebuild it later on. Deleting a variable is the same thing. We delete it from the cache. maybe we need to delete it from the optimizer. If the optimizer doesn't support it, we throw away the optimizer. And then when we come to optimize, we say, hey, we've got this caching optimizer. Do you have an optimizer attached? If no, error. If you are attached, we want to optimize from highs. Otherwise, we need to copy the model from that cache into highs and then solve it. So kind of coming back to the JuMP as it was, those were the kind of problems we had talked about in MathProg base. Hopefully you can kind of see with the design of MOI, we've kind of been able to work around all of those problems. Instead of bucketing models into 3 problem classes, linear, quadratic, conic, nonlinear, each solver now can declare a very fine-grained support for which functions and sets and objective functions it supports. Mixing problem classes is not a problem at all, because Nitro can say, yep, I know how to support scalar nonlinear, I know how to support second-order cone. Gurobi can say, yeah, I know how to support linear and quadratic and nonlinear. Highs can say, yes, I'm an LP, or I know how to support linear problems, and I can support quadratic objectives, but I don't know how to support quadratic constraints. One thing we haven't quite figured out yet is highs can support quadratic objectives if the problem is continuous, but not if there are also integers. And so we can't deal with that when we're building the model. We can only deal with that at runtime and say, hey, that's an error. Extending problem classes is easy. We just come up with a new set or a new function. So indicator, we came up with a new indicator set. Complementarity, we came up with a new complementarity set. These now work super well. And then the in-place modification we sort with the caching optimizer. It's kind of a relatively complicated piece of code, but it manages abstracting over solvers that can either support natively in-place modification, or it throws away the optimizer and rebuilds it from scratch when it needs to. But there are a few problems with MOI. And the most important thing is to read in the small letters at the bottom, the orange script, which says, these problems are too breaking for us ever to consider changing. There will not be an MOI 2.0. We don't want Python 2 to 3. I'm speaking for myself, not necessarily on behalf of the other JuMP developers. I don't know that they saw this before I made the slides. We don't want Python 2 to 3, but if you're looking to re-implement MOI in a different language, don't copy it blindly. Come and talk to us. There's some things that we would change if we were starting MOI again from scratch. One of the things Benoit hinted at before is the indices. So we associate each variable and each constraint with an integer index. So variables, it's pretty obvious. The first variable you add is 1, the second variable you add is 2, the third variable you add is 3, and so on. Except we did not make that a rule in MOI. So you can make your integer indices anything you like. You can make it 1, 10, -3, 4. And so managing the mapping of indices to when the variable was and what column it is currently well, every solver has to manage that mapping, and there's no kind of hard and fast rule. It would have been simpler if we said all variables must go 1, 2, 3, 4, 5. The same with constraints. Every constraint within a specific function and set type must have a unique index. So the first scalar affine n equal to constraint could be 1, but equally the first scalar affine function in less than could also have the index 1. So we only care about uniqueness within a constraint type, not across all constraint types. And this means we don't actually know when a JuMP model writes down their list of functions and sets with their constraints. We don't actually know in MOI the true order in which they added those constraints. We can only figure out within the constraint type what order they added. And so this often means that we can't preserve row order when we're copying models around exactly. We had this special subtype abstract vector function, and we had vector variables and vector affine function and vector quadratic function and vector nonlinear function. Why didn't we just make it a vector of scalar functions? There was some idea that we'd be able to exploit maybe matrices or sparse matrices, but we kind of haven't. it would be an open question whether how much changes we would need to make to be able to have a vector function just be a vector of scalar functions and what pros and cons that would lead to. The biggest bugbear I have is the 0.5 and the scalar quadratic function. A scalar quadratic function is a list of scalar quadratic terms, and the diagonals either have a 0.5 in front of them or a 2 in front of them, and I can never really remember which way it is, and I often just have to try both of them or sit down on a piece of paper and work it out. It would have been so much easier instead of it being elements in a Q matrix if it was just a vector of terms. So 2x, y really meant 2 times x times y, and not maybe the 2 in the lower half of the triangle of the Q matrix with a 0.5 in front of it. And then the last thing is the variable bridges. We haven't really talked about it, but in addition, each variable gets added, and they're kind of free variables, but some of them have domains. So like CSDP only knows how to support non-negative variables. And some other variables have domains as well, and sometimes the domains are important, and sometimes they aren't. And we don't have an explicit way of representing the domains in MOI. We just sometimes look through the constraints and say, hey, you had a x in greater than 0 constraint in there, which probably means the domain is greater than 0. Where it gets confusing is if you wrote down the at variable of x greater than 0 integer. Is the domain real? Is it non-negatives? Is it integer? And this kind of gets a mess, and we don't have a good way of dealing with this. So coming back to the start, I hope this talk was kind of interesting. I hope it was useful. I hope it gave you insight into what MOI is. It's one of the largest packages in Julia. It has like 122,000 lines of code. It has a whole lot of stuff on there. We talked about the bridges and reformulating the user's problem into the solver's problem. We do that by this bridge graph with the different transformations. There's so many transformations that it's not obvious which one to use sometimes. So we have to solve a shortest path problem to figure out how to change the user's problem into the solver's problem. But it all kind of seems to work very well, and it's cool. But the code is very complicated, and it causes me no end of issue. Solver wrappers, we kind of didn't really talk about, and we didn't really talk about how to write about code that uses MOI directly. And I would kind of discourage most people from trying to write MOI directly or even write a solver wrapper. There's a tutorial in the docs for MOI that says the tutorial is called Writing a Solver Wrapper, and the first thing it says is, danger! If you are writing a solver wrapper, this is a lot of work. You should come and talk to us before you attempt it. And that's all I have, so I think we'll open the floor to questions. James.
Are you missing bridges? What do users have account to use bridges?
So the question is, are we missing any bridges, or do any people come with ideas for new bridges? We semi-regularly add new bridges. Maybe not every month, but every couple of months we add a new bridge. Often it's if we've added a new set, we need to add bridges to add that. We haven't really added recently any like different formulations for conic things. We kind of have a few basic things that work. And so most of the new bridges are because we've added new functions and sets to MOI, and then to support them we need to add new bridges as well. Benoit? Yeah, so that was more of a comment than a question, so I'll repeat it into the...
Yeah, but I think that's why the reason we don't add.
Yeah, so to summarize the comment, it's a lot of the new work in MOI since we made 1.0 happens in third party. So you can make new functions and sets in external packages, and they work with JuMP just fine. You can also write new bridges in third party packages. And there's an attribute that you can define for your solver called list of non-standard bridges that will automatically get loaded and added into that bridge graph at runtime. And so there's no need necessarily to make all of the functions and sets and bridges inside MOI. We can add them to other packages. So like in SCS, it defines a number of cones that only SCS knows about, and it defines a number of bridges from the MOI cones to the SCS cones that only SCS needs to know or care about. And then they get added when you're using SCS, but not when you're using any other solver. And so we try and add things to MOI only if they're useful for multiple solvers, and bridges if they're kind of widely useful, rather than for one particular solver.
What are examples of edges in the different hypergraph which would be automated?
So the question is, what is an example of an edge in the hypergraph to which we would give a bad weight? Yeah, so one of them is, I think one of them is the function conversion bridge, where we know one of them is, hey, I've got a scalar affine function in set. I can convert that into scalar quadratic function in set. Any set, I don't care. But it's true, I mean, a scalar affine function is a subset of a scalar quadratic function, so the bridge is very easy. But you probably shouldn't do that if you didn't need to. You should only do that if then we can retransform the scalar quadratic function into something else that the solver understands. Otherwise, you would prefer to go from scalar affine function to the set. If everything is weight 1, then sometimes we go weird ways because each bridge is worth weight 1, and if we have to do multiple bridges in a row, you can end up with weird paths that have the same weight otherwise as the obvious path. So often we don't explicitly go out of our way to add, when we add a new bridge, we don't add a weight just for kicks. We kind of wait until someone reports an issue with a model and they're like, why did it reformulate it like this? And you're like, oh, okay, I'll just go and stop that bridge by adding it to weight 10.
Whenever it's a bridge that is destroyed structure, it's more high quadratic, we don't see structure anymore. Then we see that kind of situation where it's like, okay, it makes sense to start with higher weight. And normally if it's a bridge that goes into two equivalent formulation with fully expressed,
Yeah, I think
really we don't need to.
another example is like the scalar quadratic to second order cone. Is that in there? It's still? No, that's only optional. There's only maybe 3 or 4 bridges out of the 70 something that have a weight other than 1.
And there are parents that mess up with the formulation. As you said, for instance, I don't know, one bridge that was to produce a picket.
Okay, so this is a question about, so there are some of the bridges can reformulate, say, an indicator constraint. Oh yeah, so this is a good example of the bridges that don't have weight 1. So like indicator constraint to an LP reformulation or a MIP reformulation has weight 10 because we try to prolong that reformulation as much as possible. Then, if nothing else works, we do that reformulation, but we don't know what big M to choose. So then we look at the variable bounds and we infer a big M based on the variable bounds. And if you don't have bounded variables in your indicator function, then we error. So we would prefer to bridge it some other way, like there is indicator to special ordered set. There's multiple ways you can reformulate the indicator, so we only choose the big M reformulation if everything else fails. And then sometimes it works and sometimes it errors, and if it errors, it says, hey, you're missing bounded variables, add bounds to this variable to continue. Yeah, Benoit says the other example is second order cone to PST. Harley, we'll go around this way.
We were at the highest conference, we had a talk from the Apple team.
Mm-hmm.
They've spent a lot of time doing very common user cases problems to formulate in modeling language.
Yeah.
Would that live in MOI as a function, or is that at some different
So-
sort of architectural?
Yeah, so Harley's question gets at there were a lot of like modeling tricks when we omit modeling. Ample is a great example of this, where the new versions of Ample you can write, if x greater than 0, then linear constraint. In JuMP, we don't have those. There's somehow a bridge, and I think Ample have taken a lot of inspiration from JuMP's bridges and reformulations. They have taken it a step further than even we have. The reason we haven't done that is we don't know what a good function and set representation is for if x is greater than 0, then expression, or then other constraint. We could conceivably come up with something like that. We would have to come up with the syntax in JuMP, the syntax in MOI, and the bridge. So it's an open question. It's doable, like exactly this, but they end up reformulating it into a set of indicator constraints. But they would need to know big M's, and they need to know bounds, and they need to... Miles?
Yeah, that anything we this principle is that we kind of accommodate beyond what size support. And only once there's 2,000 that support that accommodation has compressed. So I think that's
Yeah.
what was my view.
There were some questions over here. Vishwas?
Yeah, so this might be a dumb question. So does the user approve the bridge or the core does
The core does
the
so the question is, does the user have to choose the bridge, or does the core choose the bridge?
But yeah, so you mentioned that there's a path that, but can the user sort of force?
So the question is, can the user force which bridge to happen? Not really, is the answer. They can delete. The way you can force it is you can write your model, say print active bridges, and see which reformulations we chose. And if you didn't like it, you can say, I want to delete that bridge from my model, and then it will go some other way. But we can't, like at the start. There's potentially some way you could, but it's like the easiest answer is no. You have to delete bridges rather than force them into the chain. Alexi?
Is bridge the correct tool potentially to improve, for example, expression tree with the linear?
So are the bridges the right way to simplify expressions like nonlinear expressions?
And as an example, for example, in your expression tree, you have many times the same resonance there.
Yeah.
Does it make sense that it's JuMP
So-
or the user to
So the-
use expression for doing some checkpoint bit for the 80, or also potentially to remove them full color in the specification?
Yeah, so can the bridges simplify models, pre-solve them, change them around? And is it the right tool? The answer is no, because the bridges, as they are currently designed, go from one function and set to a different list of functions and set, and they can't have a loop, like a self loop in the graph. Otherwise, we would have situations where the graph says, hey, you want to add this constraint, and then it adds the same constraint, and then how do we break out from that reformulation? Like you'd be reformulating the constraint, and at some point you have to stop and say, I don't want to reformulate this anymore, I want to pass this to the solver. So maybe we could, but there's no like depth in the graph, it's just a single thing.
I have some arrow when I try to write a quadratic objective with second order form of the order with CBF, but even my
So the question is, there was an error with a model that had a quadratic objective and a second order cone in the CBF file. And I think we're using MOI directly or via JuMP.
I guess it's a jump.
Yeah, then open a bug report. I think we would have to reformulate that because
Maybe something
CBF might not support the quadratic objective. Yeah, I would have to look at the details. It's been a while since I looked at the detail.
there's some keyword like Q objective.
Yeah, so we might the file format might support it, and we might not have added support to that to the MI thing. I'd have to look at the details. Harley?
Follow-up question.
Yep.
If some masochists wanted to write their own bridge, you've got solver-specific
Yep.
bridges, what about user-specific bridges that allow you to then extend the system of bridges.
Yeah.
And you can use, someone could write all those example things and extend it into the model and use those bridges.
Is that a question or a statement, or is that a?
Is that possible, and is that something you might consider?
Yeah, so you don't need our permission to do this. The code is all public. It's all open.
Yeah,
It's
so you
third
can
party.
write a package.
So yeah, well, like we now encourage people, rather than opening a PR to MOI to say, hey, I've got my new bridge, my new function. It's like, go away and do this by yourself, and come up with all the docs, all the tests, show some example use cases, and then if it looks good, then we'll add it. And if we're kind of still a bit skeptical, you can work on it for a bit longer until it's shown to be useful.
Maybe not even for integration into the base as an extension.
Oh yeah, so then there are like there's this constraint programming extensions.jl, which adds a whole lot of things. And if a user is like, hey, I really want to add constraint programming extensions, they say using JuMP, using constraint programming extensions, and then things will work that way.
Maybe can, if you define external bridge, you can either ask the user to explicitly add them to some function, or given some of priorities, automatically, if you add a specific kind of constraints, I detect that it's a new type of constraint, and I add automatically the bridge that are needed, so that the user doesn't have to manually add them.
Okay, I think we should wrap up. Oh.
There's a limit to that failure to put in.
Yeah, so you can add new things to MOI. It's much you can't you can add new syntax to JuMP, but you have to do it in a special way. Yeah. Okay, I think we need to start wrapping up.